My name is Sumitra. It's my great pleasure to welcome here Dr. Mukhopadhyay from Utah State University. He has done some great work on developing reliable service-based systems. And of course, at Google, we have a lot of applications which are built on top of services that are hosted in distributed data centers. So I'm sure it will be of a lot of interest to us. Please welcome me. Please join me in welcoming Dr. Mukhopadhyay.
Thanks for the introduction, and thanks for inviting me. So today my presentation is about a formal approach to developing reliable service-based systems. Living in the Silicon Valley, probably all of you have heard the term SOA, or service-oriented architecture. So it has been a hot topic for the last 8 years. But critics say that it has been there for the last 30 years. So now you might ask that since the technology is already there, why do you need you? Why do you need a new approach? What new are you going to tell us? So service-oriented computing is now becoming standard in industry, and it's being used in mission-critical applications. Like the DoD has currently the vision of the gig, or the global information grid, that will coordinate the 3 services. So in such applications, of course, you need reliability. So that's one of my points. But there is more to that. So as I said, service-oriented computing has been there. But what we followed so far is the middleware or the CORBA approach. What does this approach give you? It gives you a palace. It's good to have a palace, but this palace is a monolithic palace. And there are problems with this monolithic palace. First, it takes a lot of time to build this palace. Second, if you have a problem in any room within this palace, you have to dig up that entire palace to fix it. There is no easy way that you remove one room and plug in another. So we, of course, want a palace, but we want a different kind of palace. We want a palace like this. And in case you still haven't recognized what this palace is made up of, this palace is made up of Lego blocks. So we want a palace, but a palace of Lego blocks. It should be easy to construct this palace given suitable Lego blocks, collection of suitable Lego blocks. And then if a block goes wrong, just take out that block, replace it by a new block, you're done. So these are the 2 advantages of having such a palace. There is one more advantage. So why do you need a palace? A country where there is monarchy. Suppose the monarchy gets replaced by democracy. You don't need a palace anymore. So at that point, you might need a tower to commemorate the establishment of democracy. So you need to, in the monolithic approach, you need to break down, flatten that entire palace, and construct a tower from scratch. However, here, you can just reconfigure these Lego blocks so that they become this palace, take the shape of this tower. And this reconfiguration should be done automatically, push button. So that's why we call such systems, such service-oriented systems or service-based systems, as you call them, adaptable service-based systems or reconfigurable ones. So I told you several disadvantages of the current approach and what we should aim at. One is having a component-based approach, having reconfigurability, having reliability, and so on. So what we have developed, let's introduce the core technology that I'm going to introduce here, is a way of developing service-based systems that takes information from different data sources or services, integrates them, automatically figures out the logic to integrate them from the specifications, and then can send out the results to different receivers. So that should provide intelligent, dynamic, reliable information management. So the current service-oriented architecture as it is doesn't support intelligent agents. So there are several applications of such a framework. Of course, there are the usual enterprise applications. There are other applications like sensors and networks. For example, you can develop breakthrough technologies for wired and wireless systems deployed in agriculture, process automation, internet appliance control, security, healthcare, medicine, defense and space systems, power systems, and so on. And in the end, we'll give you such a demo. For example, one of them is healthcare, where you can embed a chip into the body of the patient that can collect information about the glucose content and so on. And then based on that information, you can automatically decide the drug to be injected and can automatically inject the drug as well. Another application is agriculture, where reliability is, and of course here I don't have to say that reliability is of utmost importance. Another example is agriculture, where you want to control the moisture in the soil, the amount of fertilizer in the soil, salinity, and so on. So you can put sensors throughout your soil, or this might be an athletic field like a golf course, where the golf course owner will tell you that any malfunction of this system can cause $1 million loss per day. So you can have these sensors that report to modes, and you can have this service-oriented system running on these modes, collecting information from all these sensors, making decisions, and transmitting those decisions to actuators for controlling the water, the sprinklers, the fertilizer input, and so on. So what we need is low-cost hardware for widespread development, and software that provides flexibility, intelligence, dynamism, reliability, fault tolerance, and fusion of data. So the agriculture market itself provides an opportunity of $1 billion. Athletic fields provide an opportunity of $500 million. Residential, $1 billion. So I don't have to convince you about the market. For example, and of course, there is a huge benefit to the society. For example, in Utah alone, a 5% improvement in efficiency of water usage in agriculture would result in 28% increase in available water. Western US has shortage of water. So this is one way of solving that problem. Another application could be intelligent management of power grid. So according to Morgan Stanley, silicon will reconfigure the grid and will make the grid a smart, efficient, and adaptive system, just as web and telecommunication systems are. And then there is a $275 billion industry. So I'll skip through more motivation. So let's first think about the requirements of such a system that can be used in these kind of applications. First, it should have adaptability. It should provide acceptable failures, overload, or damages. It should be able to rapidly reconfigure in order to adapt to users' new missions. For example, your requirements easily change in all these applications, in military applications, in agricultural applications, in power applications, your requirements change frequently. So you need to be able to adapt, like that palace needs to get converted to a tower. Security is, of course, important. I don't have to tell you how security is important. And of course, you need to coordinate, you need workflows for coordinating the different services so that your requirements are met. So these are some requirements of such a system. So far what I described was just motivation. Why do we need such a system? Why the current state of the art in service-oriented computing or service-oriented architecture is not enough. So now we start the main talk, and we'll start with motivations again. Then we start with a running example. We show the formal architecture for approach. We show a formal way of modeling service-oriented systems based on a calculus and a logic, and then we'll show how to automatically synthesize workflows that can achieve your objectives from user specifications. And finally, we'll show a demo of a power system controller using this system. So in case you are still not motivated enough, I'll motivate by authority. So in 2 years back, there was a Grand Challenges in Computing Research workshop conducted in UK, where two of the stalwarts in computer science, C.A.R. Hoare and Robin Milner, came up with one of the grand challenges in computing research as developing a science for global ubiquitous computing. And what is that science about? Develop models for systems composed of ad hoc networks of diverse components. Models need to supports context awareness, adaptive behavior, loose coupling, and security. Just the things that I told you in the previous slides. Develop calculi and logics to formalize notions of self and context awareness, migration, and so on. Develop models for acquisition, distribution, management, and sharing of knowledge, and building trust based on such knowledge. Develop new type systems, new static analysis techniques, new verification techniques suitable for the GUC, or the global ubiquitous computer. So the criteria or the requirements that I told you in the previous slides were also recognized by Hoare and Milner. So I didn't bring them out of thin air. So let's start with a small example that I'll use throughout the talk. Assume that a 911 service. So this comes from a personal experience. 3 years back, one night I had my smoke detector in my room. Suddenly at night, I think at 1 o'clock at night, the smoke detector in my room suddenly started making a buzzing noise. So I immediately called 911. She first asked me what my name was. I told my name. Then she asked me to spell my name. I spelled my name. Then she asked me what my address was. I had to tell the address. I had to spell the address. Then finally she asked me, are you within the house? So she asked me to go out of the house. So this approximately took 10 minutes. And then the fire engine came in, they inspected, and then they saw that the smoke detector just had gone wrong. It was not a danger. But I thought that if it was a real fire, by those 10 minutes I was spelling out my name and my address, I would have been burned to death. So that's why I thought of this example. So assume that you have a 911 center and an accident happens at some place in the city. So there is an observer. Somebody says that, hey, an accident has happened. He calls the 911 with his cell phone and gives the accident information along with the location. So what the 911 center would do is it will send accident reports to the 3 services: the ambulance management service, the fire department, and the police department, saying that an accident has happened, so-and-so accident has happened at so-and-so location. So what these people would do is they will in turn invoke services like the private ambulance service for sending an ambulance, the patrol car service for sending a patrol car, a fire engine service for sending a fire engine, and ask them to converge on that location. So this is a very simple system. Of course, how can you build such a system? Now my question is, how do you build such a system? And of course, this system has to be reliable, otherwise you might be burned to death, just as I would have been on that day if there was a real fire. Can we construct this system reliably from the requirements of the users? So of course, what are the requirements? So you have a set of service coordination requirements, like 911 center receives information about accident from observer. It sends accident report to the city fire department, police department, and ambulance management service. They send fire engine, police car, and ambulance to the accident location. So these are the service requirements of the. So if you ask the 911 center, they'll tell you that these are the requirements that we need for such a system. Fine. So how do we build such a system? Here is our approach. You take those requirements, call them the goal. You collect the other requirements, which we call the quality of service requirements, like timing and resource specifications. Timing specifications like saying that the 911, the police car, the fire engine, and the ambulance should reach at the accident location within 2 minutes. You provide the service specifications. What are the services that we have available? We have 3 services available: the ambulance management service, the police service, and the fire service. What do they take as input? What do they provide as output? Where are they located? And so on. You provide situation awareness specifications. If this situation arises, how to deal with it. For example, if somebody gets critically injured in the accident, you need to evacuate him by calling a helicopter. You provide security policy specifications that are for this particular application, saying that, okay, this guy cannot talk to this guy, and so on. And finally, you can provide customizable failure handling specifications, like saying that, okay, if the ambulance fails to start, get another ambulance. So you input all of these to an engine that I'll demo. I'll show how this engine is built, and I'll show a demo of the engine also. What this engine will do is, it will try to prove this goal. It's a proof engine. It will try to prove this goal from these service specifications under these timing constraints, situation awareness constraints, security policy specifications, and the failure handling specifications. So these 1, 3, 4, 5 serve as the constraints. These serve as axioms of your theory, and you want to derive a proof of this. Once you get a proof of this, what does this proof tell you? The proof tells you how all these services that are available can be combined, or how all the resources that you have available can be combined to meet your goal. So once you have this proof, what you can do is you can use your knowledge of mathematics. What is a proof? Curry and Howard will tell you that a proof is a program. Classical math. So you use that correspondence between proofs and programs to generate what we call workflow agents. So these workflow agents get scheduled, and then they get compiled to Java code, and they can be automatically deployed on the hosts of the network. So if you tell me that, okay, the 911 center is going to run on this computer, the ambulance management service is going to run on that host, they can be automatically deployed on these workflow agents can be automatically deployed on those hosts. This AS3 stands for adaptable, situation aware, secure service-based systems. So now they can start running, and since this was derived from a proof, they are guaranteed to meet their requirements provided these services behave according to the specification. But that's not real life. In real life, services might get hacked, services might shut down, services might change their configuration, and so on. So what you do is you monitor the execution, and based on the agent models, you can easily find out using a technique called model-based diagnosis. You can find out when these services are not behaving well, and you can feed it back to the system to generate new agents that use new services. So that's basically the approach. So how is it different from the existing standards for service-based systems, for example, for modeling workflows? One of the standards is BPEL, Business Process Execution Language for Web Services. So this is used for modeling and executing workflows. It lacks formal semantics and does not provide automatic service composition that we provide. OLS and web components, they provide constructs for unambiguously describing properties and capabilities of services using logic. They provide limited formal guarantees, but does not provide any service composition. So in order to develop such systems, you saw the block diagram of the system. So what do we need to develop a system from that block diagram? We first need a programming model for workflows. How do we develop programs for such workflows? Of course, I told you that there are languages for describing workflows like BPEL for WS, and I told you what are the problems with those languages. So what we provide is a new programming model for such workflows that we call the AS3 calculus. It provides a formal programming model for service-based systems. It's based on classical process calculi, like the pi calculus, if you're aware of the work of Milner, and has operational semantics that involve interactions between external actions, communication, leaving and joining groups, internal communications, method calls of named services, and can provide asynchronous service invocation, has timeouts, failures, ways of describing all these things. So I'll just briefly go through this syntax. I won't bore you with the syntax. So basically, the basic entity in such a calculus is a system that can consist of a recursive process, and a process can be one of these, which are like parallel composition of processes, a process that performs an external action, internal computation, failure process, one that handles failure, one that exports methods that can be invoked by other services, and so on. So external action like that E is for external action can involve communication, leaving or joining groups, removing firewalls, and internal computation takes place by calling methods of identified services. And I just formally describe. I won't bore you through all this. Let's go through the more interesting portion. We have formal operational semantics for all this. So let's try to just to give you a feeling of this calculus. Let me try to present this model this scenario in this calculus. So think about the 911 workflow for the 911 system. What does it do? It receives the information about the accident from the cell phone user. So it gets an accident report through this channel called TEL, the telephone channel, and then all it does is it sends out this information to these three services, which are the fire department, the police department, and the ambulance management service on their respective channels. So that's what it does. And then it comes back to its initial state. So it's a reactive system that receives this information, sends out this information, and then it comes back to its original state. Similarly, the police department would receive the information that this guy has sent, then call a dispatch car service, and if the car service succeeds in sending a car, then it comes back to its original state. Otherwise, it says that, OK, call this failure handling routine. So let me show you an execution just for, so this 911 center, this guy sends the accident report to the 911 center. 911 center sends it out to the police department, and then it behaves like 911. Similarly, the police service receives it from 911, then it calls the police car or wherever the car service for sending a car, and if in this case the car service was successful in sending a car, and that is produced as the return value. Now the question is, I typed up these processes. Can we automatically synthesize them from the specifications? I don't want to develop service-oriented these systems because there are several problems. First of all, programmers make mistakes. I don't want, for reliability, I don't want such mistakes. So I want to automatically synthesize these processes that I typed up from the specification. So how do I do that? The answer is yes. And here is an approach for synthesis of those processes that I showed you. First, you describe the services in a logic that I'll come in a moment, that along with the proof rules of the logic will form a theory of these systems. Then functional requirements of the mission along with the QoS goals are described as formula in the logic. Synthesis amounts to a proof of the requirements using this theory, and that proof tells you how those services are combined or composed to meet the functional and the QoS requirements of the customer. And these terms can be directly synthesized from the proof using the classical mathematics Curry-Howard correspondence. So the logic that we use for encoding the requirements, actually you don't have to use the logic, you can use a graphic user interface for putting in your requirements. They will be automatically compiled to the logic, is a hybrid model intuitionistic logic. Does anyone know what is an intuitionistic logic here? Does it? Yeah.
What do you mean non-classical? Not classical. It doesn't have formally. Not classical.
It's non-classical, yeah. So let me explain. Suppose I and Dr. Samadar are going to an island in the Pacific. Okay. So before going to the island in the Pacific, people tell us that these people on that island are liars. So whenever you ask something from them, you ask when they provide the answer, you ask for a proof of their answer, because otherwise they'll lie. So we land on the island and we feel hungry. Both of us feel hungry. So we think that if there is a McDonald's on that island, we can go and get some burger. But we don't know whether there is a McDonald's on that island. So I say that I am going on the north of that island, you go on the south of that island, and let's try to find a McDonald's, and then we come back, have our burgers, and come back at the same place. So while going north, I meet an islander called Alex. So I ask Alex, does there exist a McDonald's on this island? Alex says, yes. I say that, okay, give me a proof, because people told me that these guys lie a lot. So Alex says that, seeking a contradiction, assume that there is no McDonald's on this island. Then you cannot see anybody eating a fresh McDonald's burger on this island, fresh, hot McDonald's burger on this island. But there you can see, he shows a person on the other side of the street, that guy eating a fresh McDonald's burger. So that's a contradiction, hence there is a McDonald's on this island. I say that this proof is perfect. There is no doubt about this proof. This proof is perfect. So I believe him. Dr. Samadar goes on the south of the island and he meets Betty. So he asks Betty, does there exist a McDonald's on this island? Betty says, yes. He also asks give me a proof. So Betty says, follow me. So Dr. Samadar follows Betty. She takes Dr. Samadar to a McDonald's and says that here is the McDonald's and here is the proof that there exists a McDonald's on this island. That's also perfect proof. But what is the difference between these two proofs? I get a perfect proof from Alex, but I remain as hungry as I was before the proof. I don't get my burger. Whereas Dr. Samadar gets this proof, which is also a perfect proof, and he reaches McDonald's and he gets his burger and comes back. So that's the difference. So one is a classical proof by contradiction, which I got, which was useless for me. The other is a constructive proof that he got, a constructive proof that took him to the McDonald's, and he got his burger there. So we want our proofs to be useful. And that's why we don't want proofs by contradiction. So we have a logic where proof by contradiction is not allowed. How do you disallow that? You say that for any formula phi, phi or not phi is not a tautology. Tautology means it's not a valid formula in the logic. So that's why we make this logic intuitionistic. So it's a modal intuitionistic logic where there are modalities for temporal evolution, there are modalities for spatial location, modalities for communication, leaving and joining domains, and so on, and atomic formulas for describing relations among variables. So here is briefly a syntax of the logic, but I'll describe the syntax briefly because I'll use it for the running example to synthesize those calculus terms that I typed up. And you have basically atomic formulas. This can be any atomic for any name. Pred can be any name that describes relations among variables. You have atomic constraints. You have disjunction. You have the sometime modality like in temporal logic, branching time temporal logic. You have identifier or nominal mismatch or nominal mismatch. You have operators for describing knowledge. So this says that an agent that satisfies this pattern phi knows this object u. Operators for describing calling of services. Like this says that this agent that satisfies, that matches this pattern phi invokes some service, which I don't know yet, with input u, receives v as output, and that service is exported by some agent I, and so on. So as I said that we provide a constructive interpretation of the logic for process synthesis, and we have a sound and complete proof theory for the logic based on natural deduction. So let's try that running example in the logic. Let's try to specify those coordination requirements in the logic. So initially, the 911 service comes to know of two things: the accident, that there is an accident has happened, and the location of the accident. If it knows it, it will send this out, and if it sends this out, it will be known by the police department, the ambulance service, and the fire department. If the police department knows about the accident, then it should call some service that will enable it to send a police car to the accident location. Similarly for the ambulance management service and the fire department. So that's basically the specification that I stated in English in the beginning. You can have service specifications saying that, okay, there is a service called, separately you can have a service specification that states what are the behaviors of the services available. So there is one service available called dispatch AMB that sends an ambulance that says that, okay, whoever calls that service will receive AMB response as the return of that service. AMB response is a type that can say that, okay, succeeded in sending the car or failed to send the car. That can be invoked by something called X that can be invoked by an agent, and it's exported from a location by a service provider called AMB. Similarly, dispatch car, it provides PICA response, which is police car sent or police car not sent, as the return value. It can be invoked by anybody, and it is exported by a service called PICA, a private service called PICA, for example, a security company. Similarly, you have the other axioms for the other services. So how do we synthesize? So I showed my requirements. I showed what are the services I have available to meet my requirements. How do we compose these services? How do we combine these services to meet my requirements? How do we synthesize the processes that I typed up in the beginning? So here I'll show how we are going to synthesize those services. So remember, our first requirement was that the 911 service receives information about the accident, saying that an accident has happened and X is the location of the accident. So based on that, you can synthesize the following thing, that you can construct this 911 process that can receive two things along a new channel, which we call tel, because that will be ultimately the telephone channel. These two things are this accident, this string called accident that describes the accident. It's a string that describes, oh, so and so accident happened, blah, 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 blah. This car hit that car, and so on. And X describes the location of the accident. So then the next thing that we had was that it should send out, if the 911 service receives this location, it should send out that location. If it sends out this location, it should be received by it should be known to this location should be known to by the police department, ambulance management service, and the fire department. So we have two things. We have this one, and we have this axiom from the requirement. From these two, we use what we call in classical logic modus ponens to derive these things. And on this side, what we do is we synthesize, we further develop our code saying that, okay, the location will be sent out along these three channels, the channel for the police department, the ambulance management service, and the fire department. And the fire department should receive it, the ambulance management service should receive it, and so on. Police department should receive it. So far, so good. So we have synthesized part of what so this is, I'm telling, this is what the computer should do, what I'm telling you now, how it should synthesize. Part of the process. But how does it know which services to call? So in the code that I showed you, in the typed in processes, the code that I showed you, it knew that it had to call some service like dispatch ambulance to send the ambulance to the accident location. How does it know which service to call, which service to invoke? So we have to discover and compose those services. So how do we discover and compose those services? So remember our requirements. If the police department knows the location of the accident, then it should invoke some service. I don't know which service it is. That can be exported by somebody. I don't know who it is so far. That takes this X or the location as argument and provides PICA response as the return value, return type. So of course, since we have deduced this and we have this axiom, we will be able to deduce this, that this service will be some service will be invoked. Now we don't know which service will be invoked. So assume that we have been able to deduce this, that a service will be called that provides A and B response as the return type. It's called by the ambulance management service. The ambulance management service is trying to call some private ambulance company. And it's exported by somebody called A and B. So now I'll try to get another proof of this. I'll start another proof tree to get another proof of this. So for deriving this proof, I'll look at my service specifications. And this is where natural deduction comes into play. In natural deduction, what you do is you assume a formula A. And then you use your axioms to derive. You assume that your assumption in A is open. You derive something called B. Then what you can do is you can use a rule called implication introduction. What you do is you derive A implies B. Since you assumed A and derived B, you have actually derived A implies B and closed the assumption A. And that's what we'll do. So we'll assume this one. This is perfectly, we can assume this. It's a good assumption. And then we keep this assumption open, and then we have this axiom in the description of services that says that there is a dispatch A and B service that has these properties. So from this, we can prove whatever we had in the beginning. And from this proof, we actually derive you can now see that since the proof for this has come, you can say you have actually discovered the service that needs to be invoked, which is at this point the dispatch A and B service needs to be invoked that provides this kind of response. So it's basically a pattern matching at that point. So we have developed several systems using this technology. One is for agricultural monitoring, where you have, suppose, a golf course where you have developed several sensors that can sense the moisture content, the salinity of the soil, and so on. And you want to control your sprinklers. So this guy comes, the golf course manager comes and tells you that, hey, I have deployed all these sensors that report to modes on my golf course, and I want to develop a set of agents that can control this information flow. So they come to you, you provide them with an intuitive graphic user interface. They input all the requirements, and then you press a button. So this proof will be done, and the agents will be synthesized that can be automatically deployed on these modes. And then once these are deployed on these modes, they will receive inputs from the sensors. Sensors are nothing but services. By services, we can mean hardware services, software services, anything. And can, depending on the situation, can turn on the sprinkler or turn off the sprinkler or whatever is needed. Another application that we have, that I'm going to demo right now, a scenario of this application, is an intelligent management of the power grid. So as you know, that our power grid is antiquated. So it's a miracle that it doesn't fail. It's inefficient. There are huge losses on this power grid. And what they do is, for example, suppose you are running a furnace. Suppose you have a steel plant running a furnace. A furnace is an inductive load that reduces the power factor of the system to below unity. What happens is that the power that's generated by the power company is voltage multiplied by current, whereas the power that is received by the customer is voltage multiplied by current multiplied by cos phi, where phi is the angle between the current and the voltage. Now, ideally this angle should be 0, which means cos phi should be 1. So ideally the amount of energy that you generate will be the amount of energy that's received. But what happens is that when you start an inductive load, the voltage, the angle between the voltage and the current becomes non-zero. And hence there is a loss. So what power companies do nowadays is that they penalize the customer for running the furnace that lowers the power factor to below 1. But that's not a business option. So the idea would be that you deploy so how does this company, this steel manufacturer, be able to pay all these fines to the power company for lowering the power factor? How can he maintain the power factor to close to 1? So what you can do is you can get sensors like power factor meters and voltmeters at different points of the plant. So here is your plant. You can get you can provide power factor meters and voltmeters at different points of the plant. And then they can report to small modes which will be running our agents. So whenever the power factor goes below, say 1, what these modes will do is they'll start up the static var compensator, which is nothing but a compensator. So if your load is inductive, it will start a capacitor trying to balance it so that the power factor becomes, the angle becomes 0 again. So this way it will be able to manage the loss. Here is a summary where we are. We are currently, so this is actually a mashup. What I showed you is a way of generating a mashup. Google generates mashups, so we can generate mashups from specifications. You don't have to write the mashup. So we call this the sim shell, and we call this a Web 3.0 mashup, not a 2.0, because we can automatically generate the mashup completely on the fly. For example, for this power system control, we would, if the system worked, you would have seen the automatic generation of the mashup on the fly immediately from the requirements. So the next step is to get such a system, get such a mashup, what we are planning, in a chip, because you need to put chips inside these control systems. And that's why we are progressing towards now, and hopefully we'll get there in very soon. Thank you.